We'll just switch off the camera and turn it on. Okay, so good evening everyone and welcome to the problem solving session for the course coordination chemistry which is taken by Professor Debashish Ray and myself Satyaprakash Yadav. आप ये हमारा फिजिक्स कलर फ्रॉम अगस्त 2020 बैच. I'm working with Professor Satish Patil from SSU department, Indian Institute of Science, Bangalore. So about the course, it is a 12-week course. In week 1 basically we have I have solved a problem based on introduction and definition of coordination complex and classification of ligand. In week 2 we have discussed about the nomenclature. And in week 3 we have discussed what are the different kind of coordination number from coordination number 3 to coordination number 12, their geometry, and then slide with stereochemistry. And in week 4 we have discussed in detail about the structural isomerism and geometrical isomerism and um, stereoisomerism, and little bit about the coordination equilibrium. In week 5 we have discussed about some binding theory, basically in balance bond theory. And in week 6 we are going to discuss the bonding in complex third and fourth, in which basically discuss more about the crystal field theory. And then in lecture number 18 professor has discussed about the Jahn-Taylor effect, and in final lecture 19 we have discussed a little bit about the spring crossover and color. So first of all, I will just go little bit about the what is the crystal field theory and why its name came as a crystal field theory. Okay, so as those detail I have already given in the previous lecture, but still like crystal field theory, first given by Van Arcle and De Boer in 1930. Later, like different scientists has used this crystal field theory to explain like magnetic property and electronic property. Suppose in 1930 to 1950, Van Black used to explain to magnetic property and electronic property. In 1951, Leger and Cartman used to explain the color and spectrum. In 1952, Argyle, Bachmann, Jorgensen, Griffith, Neyman, so many scientists used to explain the different property like magnetism, reactivity, and stability. So coming to the what is crystal field theory? So crystal field theory, uh, it it consider the electrostatic interaction between ligand and metal, right? And okay, and the ligand are considered as point charge. So this is the like basic about the crystal field theory. In this, scientists have considered the electrostatic interaction between the ligand and metal, and they have considered ligand at a point charge. So basically, it's either it's a ion dipole interaction or dipole dipole interaction. So second thing is that why it is called crystal field theory. Previously, I have already told why it is considered at a valence bond theory, because their valence orbital are used to explain the various property of the complexes. Now, this crystal field theory is came because the so I will write just CFT is named due to interaction between metal and end ligand is similar to that in crystal between cation and right. So this why it is called crystal field theory, because the interaction between metal and ligand is similar to the what kind of interaction we have in the solid uh, or crystal, where like the interaction between an ion and cation are similar. Okay, so it considers the effect of ligand field and d orbital. Now I will just briefly draw all the d orbital. So there are 5 d orbital, 5. So there is dxy, dyz, dzx, dx square minus y square, and dz square. So xy means the lobe are between the x and y. Yz means the lobe are in between y and z. Zx means lobe are in between the z and x. And x square minus y square means it is like on the x and y. And dz square means it is along the z and so. So there are 5 d orbital: dxy, dyz, and dzx. Now crystal field theory assumes that what happens if ligands are approaching in the tetrahedral direction or in the octahedral direction. So how splitting will happen? So suppose we have 5 d orbital. Now ligand is coming. So what will happen? First energy will rise. Okay. Now, so first I will just draw what are the like this one, x, y, and z. Okay. So if ligand are coming along the for the octahedral, ligand will come along the axis of x, y, and z. Right. So whatever the lobe which are along the x, y, and z, they will destabilize, because if electron in that state, it will feel repulsion. So what will happen? The dx square minus y square and dz square will go up, means it will destabilize. And what will happen in between the orbital which has lobe in between? So here electron can, like ligand electron can easily come along the x and y and z direction. So what will happen? They will stabilize. So this is called three types. This is called T2G and this is called EG. So this T2G and EG is basically coming from the symmetry point of view. YG means zeroed, and if it is not there means non-zeroed. So G means zeroed. So for tetrahedral, this is for octahedral. For tetrahedral, what will happen? For tetrahedral, ligand are coming through like between the axis through an angle. So what will happen? The orbital which has lobe between the axis, they will destabilize, and the orbital which has lobe along the axis, they will stabilize. So what will happen? This is first 5d orbital, ligand will approach, energy will get higher. Now what will happen? This EG, this is E and this is T2. Okay, so 2 orbital which is dx square minus y square and dz square will stabilize, and dxy, dyz, and dz will be destabilized. Okay, and the between these two it's called delta O, and this is called delta T. So what is the relation between delta O, means octahedral stabilization energy, and tetrahedral? So there is relation that your delta T will be minus 4 by 9 delta O. So which is roughly like half of the octahedral stabilization energy. Now from where this 4 by 9 is coming. So for tetrahedral, we have 4 ligand. For octahedral, we have 6 ligand. So 2 by third contribution is coming from the number of ligand. How many number of ligand is there? So here basically there is 4 ligand metal interaction and here 6 metal ligand interaction. Now other 2 by 2 by 3 from where it is coming. So in tetrahedral, ligand are approaching through between the axis at an angle, and in octahedral, ligand approaches along the axis. So the another 2 by 3 is coming from the ligand approach. So that these are very long derivation from where they have got this 2 by 3. So this delta t and delta is the relation is minus 4 by 9. Now I will not go into the detail how this 10 dq, this is delta t is nothing but 10 dq, how this 10 dq is calculating, because in the question it will come and I will discuss. One most important thing is the spectrochemical series. Spectrochemical series. So what is the spectrochemical series? So spectrochemical series is nothing but when ligand are arranged in order of increasing ability to split the d orbital, such a series is obtained is called spectrochemical series. And why this name came like spectrochemicals? So this name is because this series based on the spectral property of the chemical species. So previously, like how we calculate the like 10 dq. 10 dq is basically be coming from professor have already told you like TiH2O6 TiH2O6 Cl3. So in UV visible that lambda max is nothing but 20,300 centimeter inverse, which correspond to 500 nanometer, right? So from lambda max we can calculate the wave number, and that wave number we basically calculate in kilocalorie, and finally we can calculate in kilojoule. So I will just write a little bit about the spectrochemical series. So when ligand are arranged in order of increasing ability to split the d orbital. D orbital means the 10 dq value, whatever it is coming. A series of ligand is obtained, that is nothing but your spectrochemical series, right? The question is why it named as the spectrochemical series. This name is because this series is based on spectral property of chemical species. What does means? Means we calculate the 10 dq value through the spectrum in UV feasible region. Right. So if for complex, we record the UV visual spectra, we get the lambda max. From lambda max, we can calculate to wave number. From wave number, we can calculate in kilocalorie, that is correspond to 10 dq value. And that 10 dq value, then based on 10 dq value, we find a series. I can just write those things, and finally I will just describe like how you can easily remember. So this is the spectrochemical series SCN minus, then Cl minus, then NO3 minus, then F minus, then OH minus, then C2O4 2 minus, then H2O, then NCS minus, then CH3CN, then pyridine, then NH3, then EN, then bipyridine, then anthrophenoline, then NO2, and then Cn minus, and then finally CO. So what is this? We can see that based on donor atom, so halide is the biggest in the spectrochemical series, then sulfur donor, then oxygen donor, then N donor, and then C donor. This order you can know, and based on that you can just find out that what is. So okay, so limitation in all, what is the limitation is there, I will not go now. One thing is that like what is high spin and low spin. Suppose this is the orbital. Okay, so we have, this is your delta 0, this is E0, and this is E0 plus delta 0, right? So we have, suppose this D2 electronic configuration, it can be like this or one electron like this. So in this case it will be 2E0 plus delta 0, right? In second case where we have like this one, so this we have delta 0 and we have 2E0 plus P. So what happens if your delta 0 is less than pairing energy? This has one pairing energy, so it is. If delta 0 is less than pairing energy, it's called high spin complex. High spin complex, or it's also called spin free. Spin free, and these are mostly paramagnetic. If delta 0 is greater than pairing energy, so what will happen? It will form low spin or spin paired complex. It called spin paired complex, and they are generally diamagnetic. Okay, so basically we have to see that if their delta 0 means this is less than pairing energy, so what will happen? Sorry. Okay, interruption. Okay, what will happen? Basically, electron can easily go from here to here. But if delta 0 is greater than pairing energy, so what will happen? The pairing will favor over the like electronic transition from one state to other state. So okay. So in octahedral, you can find both low spin and high spin. But in tetrahedral, there is no case where you can find low spin. So in tetrahedral, delta is always greater than pairing energy. Sorry, less than pairing energy. That is the case. Okay. So let me see. Should I go further? Like how square planar complex form, or should I go for the problem solving session because it's going too much? So can you just write in chat box? What should I follow? So should I go ahead and teach you about how square planet work? Okay, okay, no problem. I will go for the question answers. In that only I will just describe. So first question is, what is the most stable state for square anti-prismatic geometry? Dx square minus y square, dz square, dxy, dyz and dxy. Can you just write in chat box what is the... Okay, so and let me draw for the square anti-prismatic. So we have 5 dr, 4, 5. Under square anti-prismatic structure, means if ligand are approaching through this, so what will happen? First one and then two and this. So this is dz square, dxy and dx square minus y square, and finally dxz and dyz. So in a square anti-prismatic structure, dz square is the most stable state. Okay. So question number 2, like delta octahedral and delta tetrahedral are related by. Can just write in chat box what will be the answer. Can you write in chat box? What is the answer for question number 2? Just check once again. I think that is not correct. Can you check once again? And yeah. So delta octahedral will be 9 by 4 delta tetrahedral. So roughly octahedral is roughly double of tetrahedral. Why? I already told, like 2 by 3 contribution is coming from the number of ligand. Because in octahedral we have 6 ligand, in tetrahedral we have 4 ligand. So 4 by 6 is 2 by 3 is coming from ligand approach, and 2 by 3 is coming from the ligand approach. How ligand is approaching? So in octahedral ligand is approaching through the along the axis. In tetrahedral ligand are approaching in between the axis through an angle. So that 2 by 3. So delta tetrahedral is 4 by 9 of delta octahedral. But if you write delta octahedral, it reverses back. So this C is correct. Fine. Good stuff. Which of the following complexes has highest CFSE? Crystal field stabilization energy. So all are octahedral complexes, right? D. Okay. So what is the reason behind choosing the answer D? As we go down the group. Okay. Fine. Okay. Why not FeNH3 6 3 plus? Yeah. Okay. So here we have iron 3 plus. So I will just solve it. So iron 3 plus is what? D5, right? So we have 5, this EG T2G. So this is a strong field again. Pairing will happen. 1, 2, 3, 4, 5. For cobalt 3 plus is D6. So cobalt, rhodium, iridium all are in the same. So all R will be in the D6 configuration. For D6, it will be like, so 3 only, 1, 2, 3, 4, 5, 6. So this is from here, it will be minus 4 dq, and on top it will be plus 6 dq. So here it will be 5 5 multiplied by 4. This is minus 20 dq, and this is minus 24 dq. That is the first thing. So for these all three, we have minus 24 dq. But the thing is that once we go from 3D to 4D, 4D to 5D, every time we see 30 to 50% of 30 to 50% increase in the crystal field extraction energy. So the 10 dq value will be more for iridium over rhodium over cobalt. So that's why the correct answer is D. Yeah. Okay, next. The delta T of the following complexes follow the order. A is COCl4 minus 2, COBr minus 2, and CONCS minus 2. So which option is correct? Can you tell me for question number 4 what is the answer? A. What is the reason? In this there is two concepts. So first is, you can say that what is the donor atom. So here also x minus donor atom, x minus donor atom, here n donor atom. So we already know that n donor are stronger, n donor are stronger over the halogen donor. So that C will be the first. Now the question come between Cl4 minus and Br minus. Both are halide donor. Here the size of the ligand, size of the ligand, smaller the size, more the CFSE. That is the concept here. So the Cl minus As we go down in the series, size will increase. Accordingly, CFSE will decrease. So that is the concept here, and you are correct. Yeah. So these are the two regions behind the answer for 4. For the complex Cu NH363 plus, the coordination geometry will be. What is the geometry for this? No. So that is not the case. So let me just tell you. This is the special case, D9 plus strong field ligand. I will just give a hint. What will happen if we have D9 strong field ligand? Okay. So I will just read verbally. This is tetragonally distorted octahedral. So basically, the question is from the John Taylor distortion. So it's very like a famous question. Copper complexes are always distort, uh, distorted in octahedral. Why? Right. So that I will just draw the energy level diagram, like and then explain. So this is first 5d orbital. 100 tetrahedral, what will happen? 2 orbital Eg will destabilize and 3 T2G orbital will stabilize. Right. So now the question comes here. So what will happen? So if two trans ligandyl octahedral geometry, if they either move towards or away from the metal, and thus the resulting complex is considered to be distorted. So what I mean is, like, suppose this we have. Okay, wait a minute. So how to draw it, that octahedral? So this is your octahedral, right? This is your octahedral. Now if these two trans ligand along the z direction, what will happen? Either they move towards the metal ion or they move away from the metal ion. So what will happen? They will be distorted because now suppose if I give A, B and C. So A is equal to B, not equal to C. So this is tetragonally distorted octahedral. Now the question is comes, why this distortion happen? So this moment is not favored because of loss of bond energy, but it is occurring due to stabilization energy called John Taylor stabilization energy, and this is also known as John Taylor effect or John Taylor theorem. So now question come, what is John Taylor theorem? So John Taylor theorem said that for a non-linear molecule that is in electronically degenerate state, distortion must occur to lower the symmetry, to remove the degeneracy, and to lower the energy. Now we will see how. Now suppose if two ligands are moving away from the ligand. So what will happen? This 2T2G will further like split, right? T2G will further split. So what will happen? Since ligand are moving away from the metal ion, so what will happen? dz square will stabilize and dx square minus y square will destabilize. Similarly, bottom also dxz and dyz will stabilize and dxy will be destabilized. Right? Other way, other one I will also draw. So this is your T2G energy. Now ligand are moving towards the metal ion. What will happen? Then your this will further destabilize, right, like this. So here what will happen? Dx square minus y square and dz square. So here ligand are moving, okay, away from the, this is called z out, means ligand are moving away from the metal ion. This is called z in because ligand are moving towards the metal ion. Now we will fill the 9 electrons. So 1 2 3 4 5 6 7 8 9 10. So what here we have the stabilization. Suppose this is delta. So I will just write delta. So this is minus, this is plus lambda 1 by 2. This is minus lambda 1 by 2. So we are getting the stabilization of basically minus lambda by 2. Right? Okay. Yeah. That is very good question. How to know that whether it will be the jet in or jet out. So that I think people basically they see the, like they measure the bond distances, like they measure this is A B C. So they see that A is equal to B greater than C or A is equal to B less than C. From there I think they will basically know that whether it is jet in or jet out. If you are asking that by seeing the complex, how we can say that whether it will be the Z in or Z out, that I think it is difficult to know that whether it is Z in or Z out. Yeah, that is like difficult to tell, like whether it will be the Z in or Z out. Okay, so this is the uh, uh, in coordination geometry, like if we have D9 and this kind of the because of the John Taylor effect, we have the tetragonally distortions. Now if we are coming to the John Taylor theorem, so first this is the electronically degenerate state. Now this is the non-linear molecule. So what will happen? Distortion is must occur to break the symmetry, break the degeneracy. So we have break the degeneracy. Here also we have break the symmetry because previously it is OH, now it is tetragonally distorted uh, octahedral. So we break the symmetry, we break the degeneracy to lower the energy. Now we have the stabilization energy of minus lambda by 2. So that much energy we have lower. So that is the John Taylor theorem. Okay. Now the experimental magnetic moment of K3FeCN6 is 2.3 mic Bohr mu b n is attributed to. So what is the answer? The spin only value of low spin Fe, spin value of high spin Fe, and low spin value with orbital composition, high spin Fe with the orbital composition. Can you tell me that what is the answer for this question? Only two unpaired electrons are there. Okay. Okay. So let me first see. So here we see that iron is D6S2, right? Now here iron is in +3 oxidation state, so it is D5. D5. Now we have a strong field again, so pairing will happen. It will be the low speed. Now we just see the filling. 1, 2, 3. So there are two paired electron and one unpaired electron, right? So for one unpaired electron, what will be the magnetic moment? Magnetic moment is nothing but n plus 1 Bohr magneton, right? So here n is 1, 1 plus 1 is nothing but square root 2, which is 1.73 Bohr magneton, but it is 2.3. So now the question is that if 2 point, like whatever observed value, experimental value is greater than the spin value, why? Because the whatever we are measuring the experimental magnetic moment is the combination of spin magnetic moment and orbital magnetic moment. Okay, so if spin only magnetic moment is matches with the um, uh, experimental, means there is no orbital contribution, but if it is not matching, so definitely there is a orbital contribution. That is nothing but like j plus 2, so that later we will discuss once we. Okay, so the option C is correct here. Calculate the CFSU value of COCl4 minus 2. Tell me what is the CFSU value for COCl4 minus 2. Just calculate it. Yeah, correct. So I think now finally we will. So what is the value? So here we have cobalt in +2 oxidation state. So cobalt is D7S2. Cobalt 2 plus will be D7. Now we have like a 5d orbital under tetrahedral. It will rise to smash, and now it will split into E and T2. Now we will fill 1, 2, 3, 4, 5, 6, 7, because in tetrahedral only high spin complexes are possible. So this is E4, T2, 3. Now we will just calculate. So this is minus 6 dqt. This is plus 4 dqt. So we will just write what is the CFSE. CFSE is 4 into minus 6 plus 3 into 4. So this is minus 24 plus 12. So this is minus 12 dqt. So that is the correct answer. Option A is correct. Okay. Yeah. The dt absorption band of FeH2O6 plus 2 is split due to presence of octahedral geometry, static John-Taylor distortion, dynamic John-Taylor distortion, or present of trigonal bipyramid geometry. What should be the answer? Presence of octahedral geometry. Oh, that like incorrect. See, I can tell you what is happening. Like I have told, I think someone this one. Okay. So first of all, I will tell you how the DDF Jackson band is different. So suppose if it is octahedral, so you will see only one band and it is like that. But suppose if you see like uh, split, like it will be a slight hum like this. This is the absorption. So the question is why it is coming a shoulder or hump. If you see like in the absorption spectra, so you will see that there is some kind of different phenomena is there. So the question is here definitely the John Taylor effect is there. That is the first thing, and once we will go to the like Argel diagram, Tanabe-Sugano diagram, then we will see that actually how many peaks should come. That number of peak is coming means that is perfect geometry. But if there is extra peak means definitely there is a so I will tell you how, like suppose there is a electron transfer 1, 2 and 3. That three electronic transition can be possible. But in this case, only one electronic transition is possible. So that's why you see here, like you will not see all three peak, but you will see a slight hump on that. Means there is a John-Taylor distortion. That is the first thing. Now the question is that FeH2O6 is splitted due to. Now we will come to the, I think if professor has told you, so you will know that what actually is. So where the John Taylor distortion happened. Okay. So I think I should, okay, I will write here only somewhere. Okay. So this is the configuration of D6 D6 high spin complex, because uh, water is weak field again, high spin complex. If we see, then we will see the big John Taylor distortion. Okay. So what will happen at room temperature? At room temperature, at room temperature, because bonds are vibrating, so we can measure only average bond length. So we see very less or no distortion measurement. So all the like bond length A, B, C are nearly equal. So we can't see that there is a like a John Taylor effect is there or not. But once you go to the lower temperature, suppose we went to the at liquid nitrogen temperature 77 Kelvin. So what will happen? At that time, your vibration will cease. Then we will actually measure what is the bond length. So there you will see the two types of bond length. That is like A is equal to B not equal to C, or like greater than C or less than C. That is the like two kind of bond length you will see. So that kind of distortion is called dynamic John Taylor. So what is dynamic John Taylor distortion? It varies with the temperature. So at room temperature, we will not see any John Taylor distortion. But once we will go to the lower temperature, where we basically freeze the vibration, we see the John Taylor distortion. What is the static John-Taylor distortion? Means the John-Taylor distortion can be seen at room temperature also. So where static John-Taylor distortion you can see. So you can write like D4 high spin, D7 low spin, and D9. D9 it is high spin low spin is same. So this is strong JT distortion, John Taylor distortion, and this is nothing but your static John Taylor distortion, right? But suppose we have uh, D6 high spin, then we will see the weak John Taylor distortion. Or we have D5 also, we will see the weak John Taylor distortion. We have D4 low spin, there also we have uh, uh, John Taylor distortion. Okay, so H2 is big. Okay. You are asking what is dynamic John Taylor distortion? Okay, no, okay, fine. Oh, you are going to tell like there is a dynamic John Taylor. Yeah, correct. Yeah, fine, fine. Okay, so I think you got the question. Question number 9. Which of the following statement is incorrect? Strong field ligand have delta octa greater than the pairing energy. Weak field complexes have delta octa less than the pairing energy. High value of pairing energy implies the difficulty of um, pairing of the electron. Pairing of weak field complexes is lower than CFSC value. What is the answer? For question number 9. Just I will just check whether recording is on or not. Yeah, yeah. So I have already told, like suppose we have this one, two case. So one case it will be this, one case will be this. Okay. So this case CFSC value is greater than the lower than the pairing energy, means this is the case if delta T is greater, if delta is greater than the pairing energy, so pairing will happen. If delta is greater than pairing energy, both are things same. If delta is greater less than pairing energy, means weak field. Oh, I think I have written reverse. And this is reverse. One minute. So we have this case. So here your pairing energy means delta greater than the pairing energy. Here what will happen? Delta is less than the pairing energy. So the which one is lower, that will be the pair. Here pairing energy lower means pairing happen. Here delta is lower means electronic transition will happen. So this is the incorrect because it's saying that weak field complexes has pairing energy is lower than the CFSE value, but this is actually the high spin complex. So this is the incorrect statement. Okay. Now question number 10. An octahedral metal ion Mn2 plus has magnetic moment of 4 4 magnetron. The correct combination of the metal ion and d electron configuration are given by. What is the answer for question number 10? So I will just start right. Fe, this is the D6, this is D5, this is D3, this is D7, right? You can just make all the octahedral one. So this is D4, 1, 2, 3. It's saying T2, 4 and 2 each. So low spin complex is there. Now we have 1, 2, 3, 4. So 4, 4 plus 2. This is 24. So this will be around 4.9. Just check. Yes. Here 4, it is 4.9. Now D5, it has all 5 unpaired electron. So this is 5. 5 plus 1 means 30. This is 5.92. This T3 will be 3 unpaired electron. 3 3 plus 1. So 12. This is 3.87. And this is D5. So it is having how many? 3. 3 3 3 plus 1 is also having 3.87. Now the question is, if it is having 4 magnetron, so why the correct option is cobalt 2 plus T2G5 Neg. So that is coming from the orbital contribution. Whatever it is. Okay. So let me go to the next question. The GOI valence can directly measure the. What is the answer for this question number 11? This I think you can directly tell. Can you tell what is the answer for question number 11? GOI valence can directly measure. No, that's not the correct. So GOI valence is basically what we measure. We measure the gram susceptibility. So how we measure directly? So basically we measure the empty weight filled on. So first thing we measure the empty. There is 2 1 filled on, filled off, filled off. Second thing is that we take the sample, and here also we measure the on, filled off. Okay, and through the formula we first measure the chi, that is called gram susceptibility, and if you multiply it with the molecular weight, basically you will get the molar susceptibility. If you multiply chi m with T, basically you give the mu 50 overnight. So that is the the correct answer is gram susceptibility. We can measure direct gram magnetic susceptibility, that is chi g. A metal forms two complexes in the same oxidation state. In one complex, the magnetic moment is 4.9. In other it is 0 Bohr magneton. Which of the following metal fit to this description? That question is coming from, I think soon you will know from where it is coming from. Can you tell the answer for this question? A metal forms two complexes in same oxidation. In one complex, the magnetic moment is 4.9, and in another it is 0. No, that is not the. So see, there are two types of complexes. One complex has different, another result. So basically, this question is from the spin crossover phenomena. So the changing of spin from one state to another state, that is basically your spin crossover phenomena, and that factor it depend on three things. One is the nature of the metal ion, so that the question is nature of ligand, that maybe we have question or not, I don't know correctly. And third thing is the temperature, where you change the temperature and then find out the. Now this is the nature of the, suppose I am coming on the nature of the metal ion. So nature of the metal ion, we have D1, D2, D3, D8, D9. There is no change in spin, no change in spin, no change in spin in high spin and low spin complexes. So if a metal ion which has this configuration in low spin and high spin, they are both are same. So where the difference is there? So we have, if we have D4, we have D5, D6 and D7. These are the metal ion. They show the spin crossover phenomena, because in low spin and high spin it has the different phenomena. Now the question is, so chromium 3 is what? D3. So that fall in this region, cancel. CO2 plus, CO2 plus, in which form it will, CO2 plus is basically your D7. So D7 can show the spin crossover phenomena. Iron 2 is D6. D6 also can show the spin crossover phenomena. And this is D8. So D8 will not show the spin crossover phenomena, because in high spin and low spin they have both the same magnetic moment. Now we have to find in these two which will fit. Now we take the D6, suppose 1, 2, 3, 5. So we taken the D6. Now we fill low spin 1, 2, 3, 4, 5, 6. So there is how many number of unpaired electron? 4. So what is magnetic moment? 4, 4 plus Nn plus 2, right? 4, 24, which is nothing but your 4.9. That is the first case. Now we take the high spin. So I will just draw in the opposite direction. So what will happen? 1, 2, 3, 1, 2, 3. Total 6. Here 0, 0 plus 2 is nothing but your 0. Right? So this is the D6 which is having, if it is the high spin complex, it will give the magnetic moment of 4.9. This is basically mu s. Spin only magnetic moment 4.9. If it is low spin complex, it will be the 0 moment. So in spin crossover phenomena, there is three way it can be possible. First is the nature of the metal ion. So I have already told you, like D1, D2, D3, D8 and D9. If metal are in this configuration, no spin crossover phenomena. D4, D5, D6, D7 can show the spin crossover phenomena, because in low spin and high spin they will give the different number of the uh, mm, a different number of the unpaired electron. I don't know that whether we have, so nature of the ligand basically CS2NET. This kind of ligand will show the like different kind of magnetic moment. They form high spin and low spin both. That I think not discussed now. Maybe next class I will make one question and put it here. And second thing is the temperature thing. Temperature thing we will discuss later. Okay, now the question number 13. The correct order of delta octahedral for given complexes. We have COH2O6 2 plus, COH2O6 3 plus, FeH2O6 3 plus, FeCN6 3 minus. What is the correct order? Just tell me the answer in the chat box. Anyone can tell what will be the order? And I will just tell what are the different kind of concept here is to find out the correct answer. I will just wait for 1 minute. Okay, D 4 3. Okay, no, I think that is incorrect. B 1 3 is correct. I think yeah, that B is correct. Okay, can you tell me what are the concept you have used to tell that B? Why you are saying that B is correct? Okay, so I have written the spectrochemical series. That is the other thing. So we will see that what is the difference. Yeah. What is the difference between the first and second? So in first, that metal is in +2 oxidation state. In second, yeah, in second, metal is in the +3 oxidation state. But water is weak field ligand. Weak field ligand. Weak field ligand. Here, iron is in +3 oxidation state. But again, water weak field ligand. Now, iron with iron here also 3 plus, but Cn minus is there, which is strong field ligand. So strong field ligand will come first. So means fourth will be the highest. Now the question is second or third. Now this is a like very important question you will see in that net JRF also. Cobalt 3 plus. Cobalt 3 plus with water are O donor ligand. It always forms the low spin complex. Means their delta is higher than the pairing energy. So that's why the second place, second will come, and then this is in 2 plus, this is in 3 plus. Obviously, 3 will come first and then first will come. Because once we increase the oxidation state from like suppose M2 plus to M3 plus, we will see the 20 to 30% enhancements in the enhancements in the crystal field structure. Yeah. Okay. So the correct answer is B. For the below given complex of 3D metal ion, the ideal octahedral geometry will not be observed in. So now tell me in which case ideal octahedral geometry will not be not observed. Can anyone tell? No, that is not correct. Any other? Okay, so first I will tell that ideal octahedral geometry is not present means there is John-Taylor distortion. So I already told what is John-Taylor theorem. So I will just write D4 high spin, D7 low spin, D9 they will give the strong John Taylor distortion. D1 D1 will give the big John Taylor distortion. So now we will see the what are the possible things. So Ni is what? Ni is D8 weak field, weak fielding. So in this case, there is no distortion at all. I have already I will not go to that where that is too far. So I have already drawn the John Taylor distortion. If you feel that D8, you will see that what is John Taylor theorem said. John Taylor theorem said that for a nonlinear molecule, if there is a electronically degenerate state. So here there is no electronically degenerate state where where if distortion occur, then we get the we are lowering the symmetry and we are lowering the energy. In D8 case, it is not possible at all, right? In Mn2 plus, in Mn2 plus, we have D5. Okay, so D5 with D5 with high spin this is high spin, right? D5 with high spin complex, again there is no John Taylor distortion. Why? Because that again thing, that rule will not valid. This is CrH2O6. So this is D3. D3 low spin, again there is no John Taylor distortion because it's a D3, all three will be in the attitude. Then TiH2O6 plus 3. So this is D1 and this will have the big John Taylor distortion. So that is the correct option D. Right? Why D1? Okay. Why D1? Okay. Let me just go to the where I know. Okay. Got it right? D1 will once if we remove the symmetry, what will happen? We will get minus 2 delta by 3 stabilization energy in this case. Right? So that is the case. If electron is electronically degenerate state, it will uh, basically lower the symmetry and lower the energy by the distortion. Okay, so this things. In a square planar coordination environment, the energy ordering of 5d orbital each. Yeah. Okay. In next question is in a square planar coordination environment, the energy ordering of 5d orbital each. What is the energy order for square planar complexes? Can anyone just comment on this? Can anyone just tell which is the correct answer for this one? Question number. Hmm. Correct answer is D, dx square minus y square dx by dz square. Yeah, correct. Should I go ahead and show you how it is coming, or you can got it already? So just uh, I will just briefly explain. So this is the 5d orbital. Okay, so this 2 then T2G. Now what will happen if two ligand along the z direction is moving away, basically z out? What will happen? Dz square will get stabilized and dx square minus y square will be destabilized. Similarly here what will happen? Dyz and dzx, where z component is there will stabilize and dxy will again destabilize. Now what will happen if we completely remove that ligand along the z direction? So basically you will get the square planar. So what will happen? The z square, this orbital further will get this stabilized. This will get further destabilized and this get further destabilized. So dx square minus y square and this will further stabilize. Yz and dzx. That is the correct. So what will be the value? This is minus 5.14 dq and this will be minus 4.28 dq. This will be plus 2.28 dq and this will be the 12.28 dq. So this the distance between this is 10 dq. Okay, so this is the correct answer. So first thing is that this is octahedral, this is John-Taylor distortion, and this is square planar. Next question. The correct placement of the ligand in their order in the spectrochemical series. Can anyone just tell? Like what is the correct answer for this? It's like very simple rule what I told. Yeah, that is correct. So first we have to see highlight donor is the biggest, then S donor, or after that O donor, then N donor, and then C donor. So here first is N donor, then second is O donor. Now third concept is there Br and Cl minus. In this case, we see the size factor. Smaller the size, like they will be the stronger the ligand. So Cl minus will come, then Br minus after that. Correct. Among the following four complex, the only one correct combination of the complex is the color of these complexes. What will be the color? Okay, so this third, see, this is the correct answer. I think this is the okay, this is very like important complex. People know that this is the correct color. I think I will not go into the detail because there is not much concept here. So, it's by heart yet. The light pink color of COH2O6 plus and deep blue color of COCl4 are due to the. That is the important question. Can anyone tell what is the answer for this light pink color of COH2O6 plus and deep blue color um, for CO? Hmm. Anyone else? Why you are saying it? D? That is also not correct. Hmm. So the correct option is C. So first thing is that this is octahedral and this is tetrahedral. So based on the splitting only, you will see that whether why it is light pink color, why it is blue color. Now second thing is that you have come like uh, uh, A if you are saying metal to ligand charge transfer and you are saying D if ligand to metal transfer. So where these things happen? If you have ligand to metal charge transfer, so your metal should be in low oxidation state. Low oxidation state. Then only it can accommodate that extra electron. It's already that cobalt has that cobalt 2 plus and cobalt, both where cobalt 2 plus is there, right? So that like ligand to metal charge transfer you can't. Metal to ligand charge transfer means uh, sorry, Yeah, it should be. Sorry, I have told you other way. Cobalt, like for metal to ligand charge transfer, metal should be in low oxidation state, right? Like so that it can donate the electron easily. And for ligand to metal charge transfer, metal should have the higher oxidation state so that electron can easily, like uh, uh, ligand can easily transfer that vacant orbital of the metal. But here cobalt is a normal oxidation state plus 2 plus 3. So here you can't see the ligand to metal or metal to ligand charge transfer, right? But if we see the, like higher oxidation state, for like suppose if you have Mn7 plus or like Cr2O7, these are the case where metal are very in higher oxidation state. That's why ligand to metal charge transfer happen. Or if you have uh, ligand in low oxidation state, that example currently I am not showing, but where metal in the low oxidation state, you will see that metal to ligand charge transfer. Basically somewhere case that CO like MCO X kind of complexes. Okay, so in this in both case DD transition is there, but one is the octahedral, another is the tetrahedral. Okay, so the next question is the magnetic moment of octahedral CO plus is 4 mu b. The electronic configuration of the complex. Okay, why DD transition in the COH2O6? Okay, so COH2O6 is what? D7. So we have electron like this 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. This electron can transfer from here to there. That is the D to D electron transfer. That is the DD transition. Right? Yeah. So the magnetic moment of octahedral CO plus 2 complex is 4 mu p. The electronic configuration of complex is. What should be the like electronic configuration of the complex? This we have seen like previously also one question is similar, but this is the other way to ask the question. See. Can anyone just draw on the pen and paper? C T2G and EG3. Okay. Let me just draw all the configuration. Firstly, 1, 2, 3, 1, 2, 3, 4. We have other. Sorry, there's 3. 1, 2, 3, 4, 5, 6, and 1. This is the A, this is B, and C is at T2G4. 1, 2, 3, 4. 1, 2, 3. Okay, and so C and T is 1, 2, 3, 4, 5, 6, 7. Now just option C. Okay. Now, do you think that this is favorable? Obviously, the answer is no. Why? Because electron pairing can't be happen at higher energy level because that crystal field esteration energy will be very low. Do you think that B will be favorable? Yes, favorable because it is in the low spin complex, but the magnetic moment will be 1.73 only. But we wanted 4, so that is also incorrect for in this question. For C, do you think that again this T2G4 and EG will be the like possible configuration? No, because electron can't be paired like this is excited state, but this is the correct configuration T2G5 NEG2. This is low spin complex. One electron, all the 5 are d orbital filled, then again 2 electron will fill the Ag. Yeah, right. So the correct answer is D. Okay. Now I will go to the correct order of delta zero for the below given complexes. I think this we have solved previously, right? This is a strong field ligand, then this CO3 plus, and then FeH2O3 plus. Then I will not. Among the following, the complex ion would show the strong John-Taylor distortion. So I have already told which metal electronic configuration will show the strong John-Taylor distortion. Right? Already told you. So just see the configuration and let me know the correct answer. Among the following, the complex ion that would show the strong John-Taylor distortion is anyone can write in chat box what will be the correct answer for this question. See. Okay. No, that is not the correct answer. What I told previously. D4 low spin. D4 high spin. D7 low spin. D9 because there is no high spin and low spin will show the strong GT. Example D4 is chromium plus 2. For D7 we will have the cobalt 2 plus but with strong field ligand we have to have. Strong field ligand we should have. D9 copper 2 plus. So we should show that where D4 and high spin is there, that is our copper. Copper is the D4 and low spin, right? If it is cobalt 3 plus, then we can see that cobalt 3 plus always for the low spin complex. That is the very famous question for this, very famous question for NetJRF and IT Jam. Cobalt, why cobalt 3 plus for the low spin complexes? Correct. So that will become D6. So there for D6 there is no John-Taylor distortion. So D7 high spin, suppose COCN6 4 minus was there, then it will be the correct answer. So got it? Let me go there. The relative crystal field splitting delta octahedral delta tetrahedral are related by equation delta tetra is equal to x delta octahedral. The magnitude of x in the above. This I think we have already discussed. Yeah. The correct answer is C. 4 by 9. So 2 by 3 will come from the number of ligand and 2 by 3 will come from the ligand approach, because in tetrahedral ligand are approaching in between axis through an angle, in octahedral it is along axis. So the experimental value of K3FeCN6 2.3 mu p is attributable to. I think this also we have solved, right? Yeah, the correct answer is low spin with orbital combustion, because orbital contribution is there, that is J plus 2 that we will discuss. Okay, in tetrahedral complexes absorb 500 nanometer. What will be the respective octahedral crystal field splitting energy? Can anyone tell? I think you have to solve it. So let me solve it. Okay. I think I need one calculator. Okay, so tetrahedral complexes, the tetrahedral complex absorbs 545 nanometer. What would be the respective octahedral crystal systems? So first we will contribute the wave number. What is wave number? Wave number is nothing but 10 to the power 7 lambda in nanometer. Okay, so 10 to the power 7 divided by 545. So this will give you the wave number. Just let me calculate through the calculator. So 10 to the power 7. So I will just take 10 to the power 5 is 1000 divided by 545. So it is coming around 18,348 centimeter inverse. So we can say that, okay, 18,350 centimeter inverse. That is the wave number. Now if you want to calculate in the kilocalorie, so what is the 10 dq? 10 dq is 18,350 centimeter inverse. Now if you want to calculate from wave number to the kilocalorie, what is the formula? 351 centimeter inverse is nothing but your 1 kilocalorie. 1 kilocalorie. So now I will just write. So we have to divide A18350 divided by 351. So that is correspond to the 52.27 kilocalorie. Now we have to calculate from kilocalorie to kilojoule. 1 kilocalorie is 4.18 joule. So what will be there? We just multiply it by 4.12. 5227 multiplied by 4.18. It is 218.48 kilojoule. Right? Now this is the crystal field splitting energy. Then okay, now this is delta T. So what is delta O? Delta O will be 4 by 9 into delta, sorry, 9 by 4 into delta T. So it will be 218 multiplied by 9 divided by 4. 490.5 kilocalorie. And the option is not matching. So that should be the octahedral stabilization energy. But I don't know why it is not matching. I will see and let you know. Okay? Because I don't know why it is not matching. Sorry. It is kilojoule. Yeah, it is kilojoule. Not kilocalorie, centimeters to joule. Yeah, that's fine. 351 centimeter is 1 kilocalorie. So accordingly, we get the kilocalorie, then we can convert in 1 kilocalorie to kilojoule by multiplied by 418. Okay, so I will just see why the details are not matching. Okay, for me, I think this should be the 490 kilojoule, means 4.9 into 10 to the power 5 joule. But I don't know from where they are getting minus 16, which is absolutely like For the time being, I can see that this is not the correct option. Okay, so you can see, I will just see once again and let you know in the next class. The DD absorption band of FeH2O6 plus 2 is split due to. I think this we have already discussed, that is the dynamic joint Taylor distortion. Okay, okay. So I think this is the end of the question. So, okay, please let me know if you have any question. Do you people have any question? Yeah, you are correct. That is the dynamic joint Taylor distortion. Yeah, yeah, thank you. I will just stop.